So let's start with particle accelerators. And let's write that to study the structure of matter, we need particles moving at high speeds, or maybe velocities, okay? High velocities means high energy and momentum, right? Because remember that energy is 1/2 mv squared, kinetic energy, and this is also equal to p squared over 2m, and p is mass times velocity. So high velocity means high momentum means high kinetic energy. So now, why do we need that? Why do we need particles to travel at high speeds? It's for two reasons. The first one is that at high energies, actually, let's start with saying why low energies do not work. So at low energies, particles just bounce off of each other, usually because they are charged. So for example, if you send two protons towards each other and the energy is not high enough, their Coulomb repulsion will not make them interact, so they will not really come close together, so they hit each other and they crash, and other particles are produced because of this collision. So you need really high energies to overcome this bounce off of particles, okay? So we need energies high enough to bring particles close together so they interact. So how close together? About 10 to the minus 15 meters. And for those of you who remember, that's the size of a nucleus. So if particles come this close together to each other, the strong nuclear force will make them interact and produce new particles, okay? So that's the first reason. The second reason, let me turn the page. The second reason is that lambda is h over p, right? So the second reason is related to the de Broglie wavelength of particles. So all particles are also waves with wavelength given by de Broglie equal to h over the momentum. And since energy is p squared over 2m, comma, then lambda is h over the square root of 2 times the mass of the particle times its energy. Also, we can write energy as equal to h squared over 2 times the mass times the wavelength squared. Okay, so every particle has an associated wavelength. So to observe diffraction phenomena, you need particles to have a wavelength approximately equal to the size of the gap they are going to pass through. So if you want to observe interference phenomena between protons and a nucleus, you need that proton to have a wavelength of, say, 10 to the minus 15 meters. Okay, so to observe let's do diffraction phenomena, diffraction or other wave phenomena. You need particles to have a wavelength approximately equal to the gap they pass through. So if we're talking about the proton passing through a nucleus, for example, let's do this example. So for a proton to diffract by a nucleus, which has a radius of about 10 to the negative 15 meters, we need lambda to be about 10 to the minus 15 meters, right? So if we use E equal to h squared over 2 m lambda squared with the mass of the proton, we will find h is Planck's constant equal to 6.63 times 10 to the minus 34 squared over 2 times the mass of the proton in kilograms is 1.67 times 10 to the negative 27, and then lambda is 10 to the negative 15 squared. So if you do this calculation, you will find 1.32 times 10 to the negative 10 joules. That's not helping because when we work with subatomic particles, it's easier to work with electron volts. So if we convert this to electron volts, we will find 822.5 MeVs. Okay, and I remind you that 1 electron volt is 1.6 times 10 to the negative 19 joules. Okay, and I'm not going to write this down, but 1 electron volt is the energy of a proton that has a charge of E, or an electron that has a charge of minus E passing through a voltage of 1 volt. Okay, so that's quite large of an energy. Okay, so 822 MeVs then is the energy acquired by one proton when it passes through a voltage of 800 megavolts. That's a lot of voltage, okay? So keep that in mind. So we need really powerful machines to set this up, and really high energies so that particles will have a small wavelength. That's the one reason. Or particles will have really high energy so that they come close to other subatomic particles and they interact via the strong force. Okay, so this is like a small introduction to why we need these strong machines. So let's talk about accelerating particles now. So we actually saw one particle accelerator already when we talked about electron guns. So electron guns are sort of accelerators that accelerate electrons, okay? So let's talk about electron guns. So electron guns are accelerators limited to accelerating electrons, okay? And remember how electron guns use thermionic emission that extracts electrons from atoms, and then you use an accelerating potential to accelerate electrons at really high energies. Okay, so that was kind of like the first accelerator we saw. But let's go to talk about the big machines used in nuclear and particle physics. So now let's study LINACs, which are linear accelerators, and cyclotrons, which are circular accelerators, okay? So electron guns can only work with electrons. LINACs and cyclotrons can work with any type of particle pretty much as far as it's charged. So these two accelerators can accelerate many types of particles. Such as protons, alpha particles, even uranium-235, etc. So when I was getting my PhD at Notre Dame University, I had an office next to a nuclear accelerator pretty much, and the guys there were able to accelerate even radioactive particles, okay? So any type of particle can be accelerated pretty much. And particle accelerators can also, LINACs and cyclotrons can also accelerate electrons. So accelerators can also accelerate electrons. And the most popular one that accelerates electrons is SLAC, the Stanford Linear Accelerator, okay? So it is used to accelerate electrons. And it's at the University of Stanford, okay? So, and another type of accelerator is the synchrotron. Those are used at CERN, for example, but they are out of scope for your class. So we will immediately jump into LINACs and take it from there. So let's talk about the LINAC. So how does this work? So we use tubes connected to an oscillating potential difference. Oops. Oscillating potential difference with constant frequency. So basically an AC current, okay? So AC voltage, okay? Like the one we have in our houses. So how does this work? I'm afraid I'm gonna run out of space here, so I'm gonna try to draw this, make it tiny so it fits. So let's say we start with a proton, okay? So let's say we have a proton. Now, this is the first tube, okay? It's a hollow tube and protons can pass through this tube. And let's say that this is the second tube, the third tube, and you can imagine a fourth tube, etc. So the point is that each tube is progressively larger than the previous one. And we connect these tubes with an oscillating potential difference, okay? So this is the symbol for an AC voltage, okay? So since this is a proton, it's positively charged, so we start with the potential difference being negative on this side, so it attracts the electron and it accelerates it towards the first tube, okay? Now immediately after the proton makes it halfway through the first tube, we switch the polarity, okay, because this is an oscillating potential, so we flip the polarity and we make it positive. And then consequently this will become negative. Why do we need to make it positive? So that it pushes the proton away from the first tube and towards the second tube. And since the second tube has a negative polarity, the proton will accelerate towards the middle of this tube. And once it makes it through the middle of the tube, we switch the polarity again. So this becomes positive, and now this becomes negative. The next tube is also connected to this oscillating potential. Once it makes it through the middle, the polarity changed. So the proton is pushed. Oops. The proton is pushed again towards the third tube. And because the third tube is negatively charged, it attracts the electron towards the middle. And once it makes it to the middle of the third tube, we switch the polarity again. I mean, we don't really switch it, it's switched automatically since this is an AC voltage, okay? So this becomes, what do we need it to be? Positive, to push the proton away again, and so on and so forth, okay? But the frequency at which the polarity changes is constant. Therefore, the proton will have a different velocity each time, so its velocity is going to keep increasing, and because the velocity is going to keep increasing, we need the tubes to become progressively longer to accommodate for that change in velocity. Okay, so we switch polarity constantly. So let's write down what we just discussed. I hope this makes sense. Guys, let me know in the comments if what I talk about in these videos makes sense, and if I need to change something. Okay, I understand that it might be confusing sometimes. So, charged particles are attracted to the midpoint of the tubes. Once they make it there, to the midpoint, so once they make it to the midpoint, the polarity reverses to repel the particles to the next tube. The next tube now attracts the particles, and in this process, the particles keep accelerating. So particles keep accelerating. Now, because the frequency of the AC voltage is constant. I'm sorry about my handwriting, guys. It must be horrible at some points. So, because the frequency of the AC voltage is constant, we need to ensure that the particles spend the same amount of time in each tube. But particles accelerate, in the tubes. Thus, the tubes have to be made successively longer. Okay, so these are the main things related to LINACs. What do you mean by how long can these linear accelerators be? So this is more like trivia. So how long can LINACs be? Okay, one example is, remember when I mentioned the Stanford linear accelerator? So SLAC is about 3 kilometers long, okay? And the frequency of the alternating current, the AC voltage, is 3000 megahertz. So frequency of SLAC is 3000 megahertz. Now, using linear accelerators, we can keep accelerating particles forever, and therefore they can reach crazy speeds, and they can exceed the speed of light, right? No, that's not true. So this next part of the video is optional, because I can just tell you that no particle can go faster than the speed of light, and as particles speed up, their mass increases, etc. So I thought that I'm gonna do a very short, very short and light introduction to Einstein's relativity, okay? But this is optional, okay, guys? You don't really need to know these things, but I feel like it's cool to know and it's helpful in your understanding of what's going on with particles and why they cannot speed further than the speed of light. So let's write this down. So Einstein's relativity is what I will talk about next. And these are high school lectures, guys. But anyway, I think it's cool to know. So we'll start with this question. Can the particle gain infinite speed? Okay, so at SLAG, as we just said, they have an accelerator. They have tubes that are 3 kilometers long. So imagine an electron getting accelerated through each tube. Eventually it will reach the speed of light, right? No, that's not what happens. And by the way, while we are at it, let's say that this is something I haven't talked when we talked about LINACs, but towards the end part of a LINAC, tubes have about the same length. And why is that? Because of what we are just about to discuss, that particles cannot go faster than the speed of light. So if this is the beginning, if this is the start of a LINAC, then the end is going to look like this. So the end part is going to have tubes that are about the same length, okay? Because you cannot keep speeding particles up. So you still have the AC voltage connected between the tubes, but the length is the same. So this is the end part of LINACs, okay? They can't speed particles further than the speed of light. So let's go talk about classical physics. So classically, let's start with something you know. The kinetic energy of a particle is 1/2 m0 v squared. And that m0 will become clear later. So that's the rest mass of a particle. So m0 is the rest mass, and rest mass means the mass of a particle when it's not moving at all, okay? Of course, in classical physics, the mass of the particle when it's moving is the same as the mass of the particle when it's not moving. But anyway, let's keep talking. So let me do the following. I can write this as 1/2 m0 c squared, where c is the speed of light, times v over c, and the whole thing squared, okay? So I haven't done anything, because if I delete this and that, I get 1/2 m0 v squared, like you guys know. But anyway, let's keep moving and solve for v over c squared. So v over c squared is 2 times the kinetic energy over m0 c squared. And m0, again, is the rest mass of a particle, rest mass when particle is not moving. Okay, so this tells us, this equation, v over c squared is 2 times the kinetic energy over m0 c squared. It tells us that the velocity can keep increasing indefinitely as the kinetic energy increases. So we can get crazy high speeds, more than, I don't know, 1,000 times the speed of light. Okay, But this poses a problem, okay, because this is not what you observe in nature. So what you observe is Einstein's relativity. So let's go to Einstein, okay. Oops, my friend Einstein. I used to be able to draw him. Let me try. How do you do that? So you start with a nose. Okay. You put the eyes here. You put the crazy hair like that. Okay. The mustache. And he has shoulders, I guess. So yeah, this is a very bad Einstein. Anyway, let me clear the page and start over. So Einstein. Okay. Einstein said that every particle has a total energy given by E total squared is equal to its momentum squared times the speed of light squared plus m squared c to the fourth. Notice that if p is 0, then we get E total equal to m c squared, the rest mass of the particle times c squared, which is the most popular equation in physics, I guess. But anyway, this is not what we need, so I'm going to erase this. Okay, so if a particle moves, has this total energy. The momentum of the particle is given by the rest mass times its velocity, which is exactly what you know, but this time we have to multiply this by this factor called gamma, okay? And gamma is equal to 1 over the square root of 1 minus v over c, and the whole thing squared, okay? So this is a dimensionless parameter because we divide velocity with the speed of light, so this is a pure number. And notice that the higher the velocity, the higher the gamma, right? And if the velocity becomes equal to c, we get 1 minus 1, 0, so we get 1 over 0, so we get gamma infinite, okay? But that's not possible. So let's substitute this gamma into the equation. So pretty much what I'm gonna do is that since P is gamma times m naught times V, I'm gonna plug this in, and I want to develop a relationship between the total energy and V over C, just like we did here with the classical kinetic energy. So let's plug everything in. I know it's scary, guys, so I said it from the beginning, this is optional, so I'm gonna write this here, optional. You don't need to know these things because only you need to know is that as particles speed up, their mass increases. But anyway, let's do this. So E total squared is gamma squared m naught squared v squared, which I took from here, times c squared, which was already there, plus m naught squared c to the fourth. Okay, so if I pull out m squared c to the fourth as a common factor, I get E total squared is m squared c to the fourth times 1 plus gamma squared v squared over c squared. Okay, and it turns out that this factor here is equal to gamma squared. Let's go see why. So let's keep the red. So 1 plus gamma squared v squared over c squared is equal to 1 plus v squared over c squared times gamma squared, which is equal to 1 minus v over c squared. So if I cast this into having a common denominator, I get this, and then 1 minus v over c squared plus v squared over c squared. This cancels, so I get 1 over 1 minus v over c squared, which is equal to gamma squared. Okay, so I'm gonna plug this in there. Okay, So E total squared is equal to gamma squared m squared c to the fourth. Okay, this is cool. Which tells us that the total energy is equal to gamma m naught c squared. Okay, so I'm gonna box this. Oops. Okay, so by the way, this equation E total squared is p squared c squared plus m squared c to the fourth is equivalent to gamma m naught c squared. So we haven't done anything. We just did algebraic manipulations. Okay. Now Einstein said, but E total is equal to the kinetic energy of a particle plus its rest mass, m naught c squared. Okay. Actually, the rest mass is m naught, and m naught c squared, as we will see, is the rest energy. Okay, so since E total is gamma m naught c squared, we find that kinetic energy is equal to gamma m naught c squared minus m naught c squared. Okay, which is of course equal to m naught c squared times gamma minus 1. So if we divide kinetic energy with m naught c squared, we get gamma minus 1. And this reminds us of what we did here. Kinetic energy over m naught c squared classically is equal to v squared over c squared over 2, right? But anyway, let's go back to this. Okay, and let's square both sides. Okay, you will see in a moment why. Actually, let me do one more thing before we do that. So kinetic energy over m naught c squared plus 1. Okay, and let's take the square is equal to gamma squared. And gamma squared is 1 over 1 minus v over c squared. This is the reason why I did this, because I want this factor v over c squared to appear in my equation. So this is equal to k over m naught c squared plus 1 and the whole thing squared. Okay, so this is a lot of algebra, so I'm gonna skip some steps and give you the final result. Basically, we rearrange this to get v over c squared is 1 minus 1 over 1 plus k e over m naught c squared and the whole thing squared. Okay, so let's gather our results together. So thus, classically, we found that v over c squared is 2 times the kinetic energy over the rest mass c squared. But Einstein says that v over c squared is 1 minus 1 times over 1 plus k over m naught c squared and this whole thing squared. So what does this tell us? That if the kinetic energy, imagine this kinetic energy becoming infinitely huge, okay, such as in a linear accelerator. Okay, so let's assume that the kinetic energy is infinite. Then we will get infinity squared, which gives us infinity. So we get 1 over infinity, which is 0. So v over c squared gives us 1. So the largest possible velocity is the speed of light. So if kinetic energy is infinite, okay, classically we get v over c is infinite, which is wrong, okay? But with Einstein, we get v over c squared is 1 minus 1 over infinity, which is 1. So v is c, okay? So if I go plot this, So let's say I make a plot of V over C squared in the y-axis, and in the x-axis I plot the kinetic energy over m naught c squared. And by the way, in a moment we will go see that m naught c squared has units of energy. So if we divide kinetic energy with the rest energy, we get a dimensionless quantity. So we get a pure number. So if the kinetic energy over the rest mass is 1, yeah, so what I'm trying to say is that kinetic energy over m naught c squared is dimensionless. So we get 1, 2, 3, 4, 5, say, okay? And V naught of, V over c squared can take values like that, okay? So let's say that V over c is 2, okay? So classically, if we plot this formula, okay, the classical formula, we get that the higher the kinetic energy, the higher the velocity, and the velocity can theoretically become infinite, which is wrong, okay? But with Einstein, we get, let me use green, we get this picture. As the kinetic energy increases, the particle eventually travels with the speed of light, okay? So, yeah, that's it. There's nothing else I want to say. So particles can never go faster than light. Yes, okay. Now, let's go talk about, yes, particles can never go faster than light, even if T approaches infinity, okay? So the kinetic energy of a particle can indeed increase indefinitely, but its speed cannot, okay? So that's the point. And this was verified with linear accelerators, okay? So, and Einstein's relativity is pretty much verified every day in particle accelerators around the world. There are many particle accelerators in countries such as the United States, England, France, Switzerland, of course, China, Japan, Korea, as far as I know, Germany, Russia, and there is one in Greece. I worked there like a billion years ago, etc. So Einstein's relativity was confirmed using LINACs, okay? Because it was observed that particles cannot go faster than light. And by the way, the optional part stopped. Now these are things that you need to know. Remember when I told you that m naught c squared has units of energy? Let's go verify that. By the way, m naught c squared gives energy, so that's why it's called rest energy, okay? So, for example, if we have an electron with mass of 9.1 times 10 to the negative 31 kilograms, if we go calculate m naught c squared. By the way, notice that m naught c squared is the same as, remember the kinetic energy is 1/2 mv squared, so you multiply mass and speed squared, therefore it makes sense that this has units of energy, right? So m naught c squared is going to be 9.1 times 10 to the negative 31 squared, and then you have, sorry, it's not squared, it's just kilograms, I'm sorry. Actually, let me erase that. Times 3 times 10 to the 8 squared, and the units are kilograms times m squared over second squared, which is joules, we get 8.2 times 10 to the negative 14 joules, which is 511 keV, kilo electron volts, okay? For a proton, the mass of the proton is 1.67 times 10 to the negative 27 kilograms. And if we do the same, we find m naught c squared is equal to 1.5 times 10 to the negative 10 joules, which is equal to 939.4 mega electron volts, okay? So when we made this plot, with the optional plot, if we were dealing with electrons, then the kinetic energy, a kinetic energy of 511 kilo electron volts, which will give you this number 1 here, okay? If we increase the kinetic energy of the electron to, say, what is 2 times 511 gives us 1022. So this will be an electron with an energy of 1022 kilo electron volts, and so on and so forth. The next type of accelerator we will talk about is called the cyclotron. Cyclotrons combine electric fields to speed up the particles and magnetic fields to bend the particles as they go around in their orbit, so that they will eventually accelerate particles into high energies. And the advantage of cyclotrons is that, unlike LINACs, in which you need a really huge, a really long line of tubes to create that type of accelerator, cyclotrons do not need a lot of space. Usually they fit in a room. Okay, so let's go see how this works. So recall that electric fields, and remember that electric fields have associated voltages with them, right? So an electric field or an accelerating potential or voltage can increase the speed of charged particles. Now, magnetic fields cannot increase the speed of particles, but they can bend them. They can force them to undergo a circular motion, right? So magnetic fields, in a sense, alter the track of a charged particle. Okay, so using these two fields in tandem allows you to accelerate particles. So let's write one more thing before we see how it works. So LINACs take up a huge space. Cyclotrons can be made to be small. Okay, and we still use, for the cyclotron, we still use AC voltage of constant frequency, like in the case of the LINAC. So we use an AC voltage of constant frequency and a magnetic field. I ran out of space, sorry. And a magnetic field. So the picture looks like this. You have what they are called Ds, because they look like the letter D, okay? So you have two Ds. This is what they are called. They have to be the same size, so let me redraw this. Okay, so these are the Ds. Okay, so this is the space where you apply a uniform magnetic field. Okay, so let's assume, so in this space here, there is a uniform magnetic field B that points into the page. The same goes for this part of the D. Okay, so these are hollow tubes which are metallic, and now these are hollow metallic tubes, and they are metallic so that you can apply an AC voltage across them. So this is the AC voltage, which has a constant frequency, and it's applied across these Ds, okay? And because it's an alternating potential, the polarity changes at all times between positive and negative. So let's assume, I'm gonna use green for a charged particle. So let's assume that I have a charged particle with charge plus Q in the middle of these okay? And by the way, something I haven't mentioned for the LINACs and the Ds is that obviously this whole thing is in a vacuum, okay? Because if there is air anywhere in this space, it's gonna stop the particle. So this thing is in a vacuum, okay? So, okay, we have a charged particle. It will be attracted to the negative side of this AC voltage, right? So it's gonna acquire some velocity v. So let's assume that it starts with a velocity 0 in the middle, okay? Now, once it enters this space between the Ds, we can use Fleming's left-hand rule with our our index finger pointing inwards because of the magnetic field. And then our middle finger points to the right because the particle travels to the right. Therefore, it's gonna feel a force. So if this is V, then it's gonna feel a force F in the center, which is gonna force it to undergo a circular motion, right? And the force is always gonna be inwards, so that's F. So it's gonna come back at the beginning where it started, and now the AC voltage should change, okay? So that now we should have the negative side of the voltage on the other D and the positive here, so that the particle will go straight. That way it will speed up, it will have a velocity v prime, which is going to be larger than v, right? But once it enters this space, again, using Fleming's left-hand rule, index finger in, our middle finger to the left, therefore the force is down, right? So the velocity is going to be v prime, force is going to be down, so it's going to force it to undergo a circular motion with a larger the radius than when it was on the right side, okay? And by the way, inside the Ds, the velocity does not change, okay? Then once it exits the D again, the polarity changes. So now we have plus there and minus there. So the particle will speed up, it will have a new velocity, v double prime, which is gonna be larger than what it started with, which was v prime. It will undergo circular motion and so on and so forth. So it's gonna keep going like that. So yeah, maybe at some point we will want it to exit this arrangement with some velocity, say v triple prime, okay? So let's make this note here that the speed is constant inside this. So constant speed inside the Ds, okay? But the velocity increases between the Ds. Okay, now let's talk about the radius of curvature for the charged particles inside the Ds. So radius inside Ds. Okay, recall that the force that makes the charged particles undergo a circular motion is a centripetal force equal to QVB. All right, and since this is a centripetal force, it should be equal to mv squared over r, okay? So we can immediately solve for r. The velocity is cancelled once, so mv over qb is the radius of curvature, okay? So as v increases, r increases as expected. Now let's go talk about something important for the frequency of revolution of these particles. So we know that for circular motion, the period of one revolution is 2 pi times the radius over v. Also, the frequency is 1 over the period. If we take the radius we just calculated and plug it into the period, we find t is 2 pi over v times mv over qb, right? So the velocity cancels, and we arrive at a period that is independent of the velocity of the particles. And since the period is 1 over the frequency, we find that 1 over the frequency is 2 pi m over qb, or f, the frequency, is q times b over 2 pi m. What frequency is that? That's the frequency that the AC voltage should have in order for the particle to always experience an accelerating potential in the region between the D's, okay? So the frequency of the AC voltage should equal 2 pi, what did we find? Sorry, QB of, okay, the AC voltage should equal QB over 2 pi m, so that the charged particles are always accelerated. And this is something that is different from the LINACs. Remember, in the LINAC case, the frequency is constant. It doesn't change. So here we have to adjust the frequency to match the frequency for the particle we want to accelerate. What I'm trying to say is that Q over M, this factor over here, is different for protons than for alpha particles, for example. So you have to set this frequency before we start the machine, pretty much. Okay? And this was the cyclotron, guys. And with this, I think I'm gonna stop this video. Okay? We talked about LINACs and cyclotrons. And in the next video, I'm gonna talk about particle detectors.